All right, I swept a detail under the rug in class today, and I've kind of decided that I need to come clean about this. Let me come clean. So this has to do with an idea called absolute convergence. So we say that a series converges absolutely if the series with the absolute values converges. Okay, and this concept of absolute convergence is important for two reasons. One is it's usually easier to tell if a series is absolutely convergent than if it's convergent in the regular sense, because all of these terms in the absolute series, they're all positive. And we've seen several of our convergence tests only work if all the terms in the series are positive. And for the absolute value series, well, they are all positive, or at least non-negative, because we took the absolute value. So that's the first thing. It's easier to test for absolute convergence than regular convergence. And the second reason that absolute convergence is important is because of this fact. So if a series converges absolutely, then it converges. And this is what I swept under the rug, but I'm going to prove it. So let's prove this. So we're going to assume that this series, sum from n equals 1 to infinity of a sub n, converges absolutely. I'll abbreviate it like that. Remember that this means that the sum from n equals 1 to infinity of the absolute value of a sub n is equal to some finite number. Let's call that finite number L for limit, I guess. Okay, and now we're going to play some tricks and prove that the original series converges. Okay, and here's how we can do it. So if we take the term a sub n, that's definitely greater than or equal to the negative absolute value of a sub n, and it's definitely less than or equal to the absolute value of a sub n, right? Because it's equal to one of these two, we just don't know which in general. Okay. Well, if we add absolute value of a sub n to each part of this inequality, some nice things happen. So on this left part of the inequality, we get 0. In the middle part of the inequality, we get a sub n plus the absolute value of a sub n. And on the right side, we get absolute value of a sub n plus absolute value of a sub n. That's 2 times the absolute value of a sub n. Okay, and this is true for every value of n, right? So if we now add this for n equals 1 to infinity, what we get is 0 is less than or equal to the sum from n equals 1 to infinity of a sub n plus absolute value of a sub n. And that's less than or equal to the sum for n equals 1 to infinity of twice the absolute value of a sub n. Now this 2 right here, we can factor that out, right? Okay. Now remember, we assumed that, so let me actually move that 2 over. There we go. Now we assumed that our series was absolutely convergent, and that means that this sum right here is the value of the absolute series, right, which we called L. So now we have 0 less than or equal to the sum from n equals 1 to infinity of a sub n plus absolute value a sub n, and that's less than or equal to 2L. Okay, well, let's observe one more thing, and it has to do with this. So 0 is less than or equal to a sub n plus the absolute value of a sub n, right, which shows up right here. So each one of these terms is greater than or equal to 0. In other words, this series in the middle is all positive terms, or at least non-negative, right? And remember, we have some convergence tests for series with non-negative terms. In particular, we can use the comparison test. Actually, I guess we don't even need to do that. Right, so this series is all positive terms, and that means that this series, that means that the sequence of partial sums, so the sum from n equals 1 to capital N, so we would call this the capital Nth partial sum. So this sequence is increasing, right? But since all of these values are less than 2L, it's increasing and bounded. Right, so this is the situation we saw a couple times in class today where we know that this sequence of partial sums never gets bigger than some fixed value. Right, here are our n values here, or capital N, I guess, capital N values. So we have a sequence that is increasing but also bounded above, so it has to level off somewhere, right? That was the idea. So that means that this sum in the middle, sum from n equals 1 to infinity of a sub n plus absolute value a sub n, this must converge. Oops, I don't need this absolute value sign right here. Okay, this must converge. So let's name its value. Let's name its value capital M. Okay. So right now we know two different series converge. There was the series of absolute values that adds up to L, and then there was this other funny series, and we know it adds up to M. Okay, so let's look at the limit of the sum from n equals 1 to n of a sub n plus, sorry, that's not what I want. Just stop there. Let's look at the limit of, as n capital N goes to infinity, of the sum from n equals 1 to s sub n of a sub n. Okay, notice that this limit that we're taking here, this is the limit that defines the value of the sum of our original series, the sum from little n equals 1 to infinity of a sub n. So figuring out what this limit is, that's our goal. If we can prove that this limit exists, then we know that our series converges. Okay, and what we can do is we can play a funny little game here. We can rewrite this as the sum from n equals 1 to capital N of a sub n plus the absolute value of a sub n minus the absolute value of a sub n. Right? This is definitely an okay thing to do. So this is the limit as n goes to infinity of, well, we can put parentheses around here, right? That doesn't hurt. And because this is a finite sum right here, we can also split up this sum. We can split it into the sum as n goes from 1 to capital N of a sub n plus absolute value of a sub n minus the sum from little n equals 1 to capital N of absolute value of a sub n. Okay? And now, right, we have the limit of a difference. Oops. Now we have the limit of a difference. Our difference rule for limits says we can take the limit of each piece if we know those two limits exist. So let's write out what those two pieces are. The limit as capital N goes to infinity of the sum from n equals 1 to capital N of a sub n plus absolute value a sub n minus the limit as n capital N goes to infinity of the sum from little n equals 1 to capital N of the absolute value of a sub n. So this step right here, this is only okay if these limits exist. Okay, but look, these are the two limits that we were just working with. We know this one is what we called M, and this one is what we called L. So both of those exist. All right, so if you look at where we started, we were finding the limit of the partial sums of our series, and we got a finite value, right? So that means that the sum from n equals 1 to infinity of a sub n is m minus L. In particular, this means that our original series converges. So the sum from n equals 1 to infinity of a sub n converges. Okay, so if a series converges absolutely, then it converges.